Okay, continuing on with the enolates, I want to now talk about this idea of non-symmetric enolates, or in essence, non-symmetric carbonyls. Carbonyls where we actually have the opportunity we can form more than one type of enolate. Here, a relatively straightforward example of that. If we look at this and we think about, okay, hydrogen atoms on the alpha carbons, the carbons next door to the carbonyl. Going this way, I've got one hydrogen atom. Going this way, I've actually got two hydrogen atoms. No, but they're alpha hydrogens either way. That means I can form two different enolates. I can react this side with a base, and I'm going to start off generic here. Remove that alpha hydrogen. And form this enolate. Or I could have my base, remove either of these two hydrogens, and form an enolate that direction. Which is different from that enolate. So two different enolates. Every time we hit this sort of situation, it becomes that question, oh, do we get mixtures? Can we control it? You know, all of the same questions. So, as you might guess, this is something we can control. Indeed, these two different enolates that we have here are enolates that we give names, and these names tell us how we can control this, how we can form this. So since I'm over on this side, I'll pick this one first. This particular enolate is what we call our kinetic enolate. If you think about this, it kind of makes sense. I have hydrogen atoms over here on a side that's less hindered. This carbon has two carbons, two hydrogens attached to it. The other side, with one hydrogen, has three carbons, one hydrogen. It has more bulkier things around there. It should be harder to get at that hydrogen than these. Plus the fact that here, I've got two choices. I can pick this one, I can pick this one. It will get me to the same enolate. So it should be faster. Odds are, this is where we'll go. Probably have already guessed. If this is kinetic, this is something that happens faster, then the other option is our other favorite term. Or maybe not our favorite term. This is the thermodynamic enolate. Now here, trying to decide why is this thermodynamic, well, we could go through and do calculations and determine, okay, heat of formation energy and the like, sure. Or, if we think about this enolate as if it's really an alkene, as if this double bond is really just there, we know actually it's delocalized over all three atoms, but if we think about it as an alkene and we think back out to alkenes, more substituted alkenes were thermodynamically more stable. Well, here I have a 1,2, count the oxygen, a tri-substituted alkene. Here I've got a 1, 2, 3, counting the oxygen, 4, a tetra-substituted alkene. More substituted option should be more stable, and indeed it is. So our more stable enolate are faster to form enolate. In terms of controlling this then, we just need to think about how do we control kinetics and thermodynamics. And this boils down to two or maybe three general reaction parameters. So if we want to make a kinetic enolate, we want whatever's going to form fastest. And to favor that, we can typically go with a short reaction time. We can also give this system as little energy as possible. So we want a low temperature. And by low temperature, we're usually talking about minus 78 degrees centigrade, really cold. The other thing we want to do is we want to make certain that this reaction goes one way and stops. We do not want it to equilibrate. So we want a strong base. Usually we'll wind up using LDA. And we want this to be aprotic. We do not want there to be a proton source left over here such that it can equilibrate back and forth. So there better not be any alcohols in here, there better not be any, certainly carboxylic acids, no proton source. That will give us our kinetic enolate. Thermodynamic, we basically take these same principles, I guess I've cut it, or divided it up into 4 here, we flip them around. We want a longer reaction time. Give this system a chance to decide, what makes me happiest? This should make it happiest. We'd like to have a higher temp. But remember, higher temperature is relative. Usually on something like this, a higher temperature means 0 degrees centigrade. Still not really high, but compared to minus 78, yes, it's high. Base, we can use either a strong base or a more modest base. So you'll oftentimes see something like potassium T-butoxide. That's in kind of the modest base category. But I do want to point out we can actually use LDA to get a thermodynamic enolate. So we can use either an alkoxide or LDA as long as we think about that last question, aprotic. I would like for there to be a proton source in here. So protic, I have to be a little careful with that term. What I want to make certain is that there is some proton source. There doesn't need to be a lot, but there needs to be at least a little bit. And so this protic idea can mean we can either have an alcohol in there. So for example, if we're using T-butoxide, as we deprotonate, we're forming T-butanol. That's an alcohol proton source that can enable it to go back and forth and equilibrate. We could also, however, use something like LDA and then add in, say, a drop of some sort of alcohol. Now that something will have a proton source in there so that enolate can react with our more acidic proton source, get back to enol, and back and forth it can go. You can also, in point of fact, simply have a slight excess of your starting ketone relative to your base, even a strong base, because that excess carbonyl form has acidic alpha protons. They can react with an enolate to basically flip-flop what was the enolate, and what was the carbonyl form. Little complicated there, trying to think through that. So I would encourage you, think through, work through these permutations, and if you have questions, absolutely ask. But this is our way that we can control kinetic, thermodynamic enolates under basic conditions.